Ladies and gentlemen, let's get into the video. We're going to be talking about Nvidia's Pascal Architecture and also some of the latest rumours concerning the GTX 1070 and 1080 as a whole. So this video is very different from my normal format, but I figured this type of format is going to lend itself much better to how I want to put together this video, as in just how fluid it's going to be. So rather than trying to edit loads of slides in, which would probably mean I'd be here until Christmas, I decided to go ahead and do it this way. So first things first, I'm looking at the white paper which is available, the Tesla P100 white paper. It's known as Pascal Architecture white paper. It's freely available from Nvidia's own website. And I've also put together this handy dandy shiny comparison of the GTX 980, 980 Ti, 1070, 1080 Titan and the GP100. Now, let's focus on these two cards first, the 1070 and 1080. So, both are going to be using 8 billion transistors, supposedly, 16 nm FinFET process on, and of course using the GP104 core, which not new information there. There have been extra leaks which confirm 8GB GDDR5 for the 1070 with 5X going to be reserved for the 1080. Now, interestingly, single pin, 8-pin, just to clarify, is supposedly going to be able to power both of these cards, which means that the TDP of these cards is absolutely titchy. You're looking at probably around 160 watts at most range. I mean, which would actually kind of go where Polaris is, because I'm hearing Polaris is going to be about 150-ish. So, that's pretty damn impressive, right? But anyway, this is of course on a 256-bit bus for both cards, which should be okay in terms of memory bandwidth once you take into account the various efficiencies. We don't know how many CUDA cores there are going to be for the 1070. The 1080, from the leaks, it's looking at 2560. So we could assume the 1070 is not going to have fewer than 2000. So let's say the low 2000 range, which makes a lot of sense. And that gap, the gap between the 1080 and the GP100, is actually quite huge. It's quite massive. But that's roughly what you'd expect, given, once again, the gap between the 980 and the GTX Titan X, which obviously are using the current Maxwell architecture. So we can presumably guess that there's going to be another card somewhere which is going to squeeze in to this lineup. So we're probably going to see the GTX 1080 Ti, and then we're going to see like a Titan as well, which obviously the 1080 Ti is probably going to have, let's say, 3000-ish cores, and then might have the full thing, which is going to have like the full 3800 cores. But you'll see more what I mean in just a moment. When we go through the Tesla Architecture white paper. There's an absolute ridiculous amount of stuff here, and honestly, it's way too much for me to go through in this video, even using this format in this single video. I'd be here until Christmas, but what I did want to go through is some of the pertinent stuff which is going to transfer over from the I guess high-end server market down to the desktop market. So let's go through this, shall we? So nearly a decade ago, Nvidia pioneered the use of GPUs to accelerate computationally intensive workloads. Now the reason that's quite interesting, not necessarily the focus of this, but back in the day when the G80 came out, which would be like the 8800 GTS, the 8800 GTX, it was quite revolutionary in terms of architecture, because before the 7800, for example, it was a pretty damn fast card, but it had inefficiencies because you would have separate geometry and transformation processes. You would have separate transformations for scene setup, and it just wasn't. It was a very static way to do things. So, for example, you could have a certain scene which didn't require so much of A, but required a lot more B, but because you couldn't get processors A to handle the tasks of B, it just meant that you had wasted silicon. You had wasted performance. So that's why they start to go to these unified architectures that we start seeing in Nvidia's cards and AMD's cards now. But it also means that those cards also lend themselves really well to compute-orientated tasks. So whether that's the GCN architecture or whether that's the Pascal architecture, that's where that started to come from. Excuse me, just grabbing some water. So Nvidia have touted a lot about the DGX1 server, which utilizes 8 Tesla P100 accelerators. That's supercomputing and not really pertinent to us, but admit you'd like one. So the key features of Tesla extreme performance, which we can assume is also going to be the same for Pascal as an architecture, although we don't know what the compute performance is going to be. But we'll see a comparison in just a second of what Nvidia believes the differences are between Pascal and Maxwell. NVLink, don't get your hopes up, this is not for desktop, but it's quite cool if you're running multiple GPUs. Basically, the problem with PCIe is that if you're running, let's say, 4 GPUs in the same system, you start getting bandwidth contention, which means that each of the GPUs are vying for the same memory bandwidth. And NVLink helps this because it's got 5 times the bandwidth. HBM2. So there are 15 billion transistors on the Tesla P100, but an awful lot of those, almost half, are actually for the HBM2 memory, but we'll go into that in just a second. Unified memory, we've talked about this a lot, and it's not really going to be for the desktop anyway. This is mostly for server-orientated tasks. Unified memory is basically the CPU and GPU address the same piece of memory. So let's say that you have the CPU is saying, I want you, GPU, to figure out what 1 plus 3 is. So, and then I want you to return that result to me. So the CPU doesn't have to copy that data to the GPU's memory. Instead, it just basically says that I need you to do that, and then the GPU gets to work on the task. The CPU basically gives up the, or rather, gives up the, I guess you could say, the lock on that memory. It will, and then so you don't get memory. You don't basically get discontention where the GPU and CPU are basically trying to work on the same thing, therefore you get a crash or other nasty things happening. A CPU will give up that piece of memory, say to the GPU, hey, you give me that result. The GPU will say, hey, what did you want to know? 1 plus 3 equals 4. Complex math there. And it will then basically say to the GPU, hey, figured out that, and then the CPU will take over that same piece of memory. We've talked about unified memory a lot in the PS4/Xbox One videos, and I've also got dedicated memory on what unified memory is. 16nm FinFET process, basically shrunk process from 28nm. It just basically means that you can fit more transistors into the same space, which is obviously a good thing because it means that we've stopped scrolling up without me telling you to scroll up, computer. This means that A, you can fit more transistors into the same space. B, it means you can cut down on manufacturing costs because the same amount of silicon can basically house more things. It cuts down on shipping costs and power consumption and lots of other stuff as well. So, deep learning, these are single precision, double precision, half precision. I don't want to spend too long on this. The main difference is that you can see an awful, massive increase in performance from the Maxwell architecture to Pascal architecture. But half precision offers twice the performance of single precision, which kind of makes sense on the face of it, but that wasn't actually the case previously. Pascal is the first architecture to do this. The main reason you would want to go half precision is if you don't need your work to be so accurate. For example, video rendering compared to modeling the universe. There's slight difference in how precise you need to be. So it's basically just floating point instructions. Like if you want to start calculating pi or something like that, then you know you're going to need something a bit more precise. Is basically where I'm going with this. I don't want to spend too long on deep learning. NVLink, I will touch upon that briefly. So, as GPU accelerated computing has risen in popularity, more multi-GPU systems are being deployed. So now many 4 and 8 GPU configurations are starting to solve bigger and more complex problems, and those are being interconnected, and then you've got basically Ethernet connections which are connecting those computers together. So you're basically making massive networks So let's say, for the sake of argument, you've got computer A connected to computer B, connected to computer C, connected to computer D, and each of those are talking to each other, all trying to solve certain problems, and each of those might be loaded with multiple CPUs and multiple GPUs, all trying to figure out or calculate, let's say, the number sequence of pi or whatever they're trying to do. So because of that, more GPUs in the same system eats up more memory bandwidth, which means you need faster ways for the CPU to address each of those GPUs, and you also need a space where the GPUs can talk to one another as well. This is really important when you start doing really complex shit, and you can start having situations where, let's say, CPU A is working on a task and it's halfway through, and then that needs to be farmed off to another CPU because that CPU that GPU is, I don't know, got some free processing space on it because it's figured out a certain task. So let's say, this is a really basic example, but let's say the GPU A is trying to, or let's say GPU 1 is trying to calculate A plus B, and GPU C is trying to calculate, I don't know, E plus F, but GPU 1 finishes its calculation, so basically you might have a situation where the other GPU can farm off some work to GPU 1 to help it with the E plus F calculation. Hopefully that made some sense. I'm vastly simplifying, but I think you get the basic gist of it. So now you could start seeing the massive difference in bandwidth with how NVLink can make a massive difference. AMD are going to be putting out their own version of this. There is some differences. It's unknown whether they're going to have a desktop version. They've not specified yet. This is only for servers. AMD's supposedly has less memory bandwidth but less latency issues. So theirs could be better for gaming, but we'll have to wait, unfortunately. Anyway, let's mosey on over. HBM2, high bandwidth memory 2. The really beautiful thing about HBM2 is A, it offers 3 times the memory bandwidth of Maxwell, but B, it also takes up a lot less space, and it also is error correction if memory serves, which we'll go through in a second anyway. So the beautiful thing about this is you've got less stuff on the PCB, less power circuitry which can distribute energy to the memory chips. You've got less PCB space, which is to actually put those memory chips on because they're on the same physical package as the GPU, which saves space, which is really handy for server clusters. But it's also nice as well if you're building gaming systems, because you might want to put in, let's say, if you look at the Fury or the Nano, look at the size of that thing and how much computing performance you can put in a small form factor system. It's kind of cool. And you can see, once again, Nvidia showing a figure there of the memory bandwidth. It's kind of a crappy figure. I wish they'd been a bit more illustrative, but it is what it is. Simplified programming for developers with unified memory. We've been through that to a degree anyway, but basically unified memory is a lot easier to I guess you could say program for, because it means you need to worry a lot less about making sure that the CPU and GPU are on the same page about actually sending data backwards and forwards to their own requisite memory pools, because otherwise you might get instances where the CPU is like, shouldn't I have got that memory back? Which is all about syncing. Basically syncing is the CPU and GPU basically saying to each other, okay, this is where I am, this is what I've done, this is what I need finished, this is what is currently in my workload pool, so on and so on and so on. So let's talk a bit about the architecture. We have touched on this previously, but I want to go more in depth into it. So this is the Maxwell architecture. This is from the GTX 980, which is pretty applicable. And then we can see the Pascal architecture. So what are the main differences? Well, essentially it's efficiency. What you're looking at is, let's read this out. Like previous Tesla class GPUs, GP100 is comprised of GPCs, graphics processing clusters, texture processing clusters, streaming multiprocessors, and memory controllers. A full GP100 consists of 6 GPCs, 60 Pascals, SM units in the GP100 are called SM units, 30 TPCs, and 8 512-bit memory controllers, which is a 4096 total. So just to go over that one more time, the GP100 is comprised of multiple graphics processors, and a full GP100 it consists of 6 GPCs with 60 Pascal units, 60 Pascal SMs, and SM units are once again SM units in GP100 called SM units with the 30 TPCs. So each GPC inside the 100 has 10 SMs. Each SM has 64 CUDA cores and 4 texture units. So with 60 SMs, the GP100 has 3,840 single precision CUDA cores and 240 texture units. Now, if all of that sounds really confusing, you could start seeing the comparison right here. Let me scroll down just a little more. There we go. That can kind of fit everything on there. So what's interesting is the die size is about the same. You only got 9 nm difference, but that's thanks to, once again, the much smaller processing size. But what's really insane here is the what figure am I looking for? I saw it a second ago. That's it. These G-flops. So peak FP64, which is the double precision. Look at the difference: 210 G-flops versus 5,300 or 5.3 T-flops. But you can also see the clock speed's a lot higher. That's both on the base and the boost clock. You're looking at about 30% higher on the base alone. And also, you're looking a lot more SMs. And basically, the numbers have gone up. So you've got a lot fewer CUDA cores per SM, which is why you start seeing that difference. Basically, what Nvidia have done is they've reduced the number of CUDA cores per SM while keeping things like the memory sizes and register sizes and that type of stuff the same. In fact, you can see that. So per SM, right here, remember the 64 SMs, the 64 CUDA cores per SM, and they've basically said, well, what we're going to do is we're going to make it so that those CUDA cores have more register memory to work with. And on top of that as well, the cache has drastically increased as well. It's gone up to 4 megabytes, which doesn't sound much, but in GPU terms, that's a lot of cache. And they've also gone ahead and boosted up the overall register file size as well over the entire GPU. It's gone up massively. It's over twice as much, which is absolutely just gargantuan in terms of difference. And honestly, it should make quite a difference in efficiency. It basically means that you should start seeing a lot less thread contention, and Nvidia say it themselves, overall shared memory across the GP100 increased due to increased SM count, and aggregate shared memory bandwidth is effectively more than doubled. A higher ratio of shared memory, registers and warps per SM in GP100 allows the SM to be more efficiently execute code, and there are more warps for the instruction schedule to choose from, more loads to initiate, and more per thread bandwidth to shared memory. Compared to Pascal, SMs features a simpler data path organization, requires less die area and less power. Basically, this card is going to be a lot more efficient. You should start seeing the GPU's pipeline being a lot less constrained. The actual processors should be, in theory, a lot fuller. Remember, GPU load, if you're running a GPU, you don't want the load, and this is regardless of workload, by the way, whether it's a game, whether it's compute, whether it doesn't really matter. You want that load to be as high as possible. So if you're developing a game and you notice that your game engine is only putting out, let's say, using an average of 70% GPU load, that's not a good thing. That's a bad thing. You want the GPU to be fully engaged, unless you're running like a really old engine or really old game, in which case you might be CPU bound. But generally speaking, you want the GPU to be as busy as possible. And that's why whenever you talk about Naughty Dog, when they're talking about, let's say, what they've managed to get out of the CPU or what they've managed to get out of the GPU, they always talk about maximizing the number of processors or the number of compute cores or whatever they end up running, simply so they can get the most performance out of the hardware they've got. Designed for high performance double precision. I think most of this stuff is not particularly pertinent. Level 1, level 2 changes, that could be handy. While Fermi and GP Kepler feature a 64 configurable shared memory, and level 1, there can be split allocation between the level 1 and level 2. The GM200 has its own dedicated pool of shared memory, and a level 1 CUDA block cannot allocate more than 64 kilobytes of shared memory by itself, but 2 thread blocks could use 64 KB and so on, etc, etc. The GP100 features a unified 4096 kilobytes level 2 cache that provide efficient high-speed data sharing across the GPU. In comparison, GK100's level 2 cache was 1536 kilobytes, while GM shipped with 3072 of level 2 cache with more cache located on chip. Fewer requests to the GPU's DRAM are required, which reduces onboard power efficiency, memory bandwidth. So basically what they're saying here is because you've got more memory on the cache, you can keep the requests, and there's more likelihood that the data is going to be available that the GPU needs, which is stored on the cache, rather than need to farm out to the GPU's memory. This once again reduces latency an awful lot. And you might think, well, 1 terabyte per second of bandwidth on the Pascal is a lot. It is, but if you're not being efficient with it, it's still going to be used up pretty quickly. And that's just how it is, unfortunately. So you can start seeing, once again, the main difference between the warps and the compute differences here. I mean, honestly speaking, there is not huge differences. I mean, it is the same in terms of the basic functionality of the GPU, but it's just a lot more efficient, and Nvidia are basically going to be much more focused on, I guess you could say, squeezing what they can out of the space they've got. World's first GPU with HBM2. I don't think there's anything particularly new here. Yeah, it's just talking about TSVs through silicon via holes. So not anything new. It basically shows how the GPU sits on the HBM2 memory. So basically all this illustration is right here is actually the GPU right there. That's the actual core, and then you've got the actual HBM memory, which is stacked either side, and then you've got the passive silicon interposer. You can think of this as just the wires where the actual memory itself connects to this. So you can see doink doink doink, that's the wires, doink doink doink, these are talking to one another. It's kind of a crude illustration, but it shows what the heck's, what's going on. And it shows as well how insane this is. Now, another benefit of HBM2 is native support for error correcting code. ECC allows higher reliability for compute applications which are sensitive to data corruption. It is especially important for large-scale data cluster computing environments where GPUs process very large data sets or run applications for extended periods. ECC technology detects and corrects single-bit soft errors before they affect the system. In comparison, GDDR5 does not provide that and is limited to error detection of GDDR5 bus only. Errors in the memory controller or DRAM are not detected. Now, this is probably not going to necessarily affect you as a gamer, because HBM2, because it's got native ECC, it will eventually farm its way down to GPUs that you're going to buy for, let's say, playing Quake on, but it's probably not going to necessarily make a massive difference. Maybe some developers will use it. Who knows? This is the close-up, of course, of the GPU, where you can see the various components of the GPU, including, of course, the HBM memory and the actual core itself, which looks rather lovely. Kind of curious to see what it looks like with the cooler on it. So now you've got high-speed connect, which we've already gone through to a degree anyway, so I don't think we need to go over that again. I think that's about all I wanted to talk about in this particular video. I'm just quickly scrolling. This is all coding and way, 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 way outside the remits of this video. Yeah, the learning. I believe I had actually already looked at this one more. I had already looked at this white paper previously, so I knew what I want to talk about. I just want to make sure that I'm not forgetting anything. I think that's just about everything. Yeah, cool. Well, hopefully you've enjoyed this less formal look. Now, most of the stuff we have kind of touched upon anyway, but I just wanted to really throw it out into one video now. We've got this white paper released. Let me know if you've enjoyed it. It's been a bit of a different one. It's been a bit of a well, let's say less constructive one than normal. Normally we've got everything kind of, I normally have everything planned out, but I decided to do things a bit more organically. So let me know your thoughts on this. Anyway, hopefully you've enjoyed the video. I'll see you soon. Take care. Bye for now.